Hey guys, this is Josh, and today we're going to talk about relativity. Specifically, we're going to talk about the equivalence principle. And then we're going to get to some more interesting topics in physics, such as quantum gravity. And I'm going to try my best to explain to you guys in very basic terms what's going on right now in the recent development
2 hours later
and the current work. Okay? So, let's do it. So the beginning of our story starts with old Isaac Newton, okay? And Newton came along and created a theory of gravity. It's called the Newtonian theory. So what he said was, if we have a particle, then it experiences a gravitational force. Its position r is governed by this differential equation. And in his Newtonian theory, we understand gravitational attraction, which is if we have two masses, m1 and m2 over here, then they're going to be pulled towards each other. But there's already some problems with this. Why? So the main problem that we see over here is that these two masses are getting pulled to each other. That's great. But how does this mass know that this mass is there? There's some sort of instantaneous action at a distance that this mass gets pulled towards that, which nothing can travel more faster than the speed of light. This mass is instantaneously getting pulled towards this one. Problem number 2. In Newtonian mechanics, space and time are treated on completely different footings. Think about it like this. Like the first chunk of space that I have over there with the smiley face, think of that as the New Year's Eve of 1955, okay? It's one flat sheet of space for one instant in time. And then as time goes along, you have another flat sheet of space and etc. But you see, space and time here are not the same. They're really not. Time is just playing a very passive role, while space is the dominant one in this theory. So Einstein's grand solution to this became the birth of special relativity. And in special relativity, we have space and time into one entity called space-time. And we get a bunch of cool consequences, such as these things over here called light cones. Okay, so this is great. Now we have space and time unified into one theory. But the real question is, how do we still explain this action at a distance? How does this mass 1 know that mass 2 is there? How does it communicate with each other? In comes general relativity. Boom, boom, boom. Now we have a full theory of the dynamics of space-time itself. On the left side here, we have this R and this G, and this all explains the geometry of space-time, okay? So for example, like a sphere. You have a sphere, it has a geometry that you can describe. And on the right side here, we have this T. This T is called the stress energy momentum tensor. So what's going on here really? In this theory of general relativity now, as I said before, we have this famous statement that mass, so all this stress, all this energy, mass tells space-time how to curve, and space-time tells mass how to move. So it's like a dynamic going on. So you can see here, we have this slice of space-time, and we have this big chunk of mass, okay? And this big chunk of mass will distort the space-time in some way. It will cause a little dip, like a trampoline. You ever been on a trampoline, you jump on it, it dips a bit because of your mass. It's the same thing here, but for space-time. So this chunk of mass will distort the space-time. And if we have a mass here, like a little guy, let's call it little m, okay? Now we don't have action at a distance. But we have another statement that massive particles, or particles in general, will follow the path of least action. It's called the principle of least action. And you can see that it just wants to fall here. This is the easiest path. And this makes sense, because if you consider like just a flat space-time, and the distance between 2 points, you know that if a particle starts here, it's gonna go in a straight line here, assuming there's no gravity, okay? And this makes sense because it's just flat space. But if you have curved space-time, then massive particles, they will follow paths of least action. they're gonna find extremums. And that's how there's no more action at a distance. It's rather that these particles, they follow the geodesics. So that's great, right? You guys feel like you know it all now. We have a mass, we have an equation that tells us how to move. It's called the geodesic equation. We know everything, right? But how did this come to be, right? How did this come to be? It all started from this important principle called the equivalence principle, which I'm gonna explain right now. So think about this experiment real quick. It's called a thought experiment. And this is something Einstein did a lot when he was coming up with this theory. So think of a guy in an elevator, okay? And this kind of like frame that we're talking about here is called a local inertial frame of the elevator. So it's only narrowed down to a little segment of the elevator. Nothing else, okay? And imagine this elevator, it's accelerating upwards. Now the equivalence principle says that you cannot tell the difference between an accelerating frame and a frame with gravity. Because think about it. If you're in an elevator and you're accelerating upward, let's say you're accelerating at the speed of gravity, 9.81 meters per second squared, your feet will be firmly planted on the ground and you will experience a normal force. And you cannot tell the difference. Let's say you have all your instruments that you want. You won't be able to tell the difference between your acceleration and just standing on Earth. Okay? And on the flip side, let's say you're in an elevator and you're in free fall. So that's the bottom scenario over here. And you're in free fall, let's say for gravity, like the 9.81 again. You won't be able to tell the difference between that and no gravity. So free fall is completely equivalent to no gravity. And if you stop to really think about it, this makes a whole lot of sense. But you still might ask, how do these connect the dots? How do we get from this equivalence principle to Einstein's equation? It seems like a big leap, but it's really not, because let me explain. So the equivalence principle says you cannot tell the difference in a locally enough region, in a small enough region of space-time. Can't tell the difference between accelerating frame, and a frame with gravity. And we know the physics of accelerating frames. We know the physics of acceleration. And we know via this equivalence principle that acceleration is exactly the same as gravity. So if we figure out the physics of acceleration, we find out that it's exactly equivalent to the physics of curved space-time that we have over there. So acceleration, the physics of it, mathematics, is linked to curved space-time. So curved space-time is then the governing dynamics of gravity. So curved space-time is gravity, and then we get this famous saying that mass distorts the space-time and curves it in a sense. Mass tells space-time how to form, and space-time tells mass how to move via these geodesics. So those were the basics of general relativity, of special relativity. You're good to go. Now we can talk about the really interesting stuff. But keep in mind this whole time that it all stems from the equivalence principle. Without that, if that was proven to be incorrect, there's no general relativity, there's nothing. Keep in the back of your mind that everything stems from the equivalence principle. So the big problem that we have here is that we now have a divide in physics. We have, on the left-hand side, we have general relativity, which I just talked about for the past who knows how many minutes. But general relativity, it describes black holes, it describes the dynamics of space-time, it describes very supermassive bodies much greater than the mass of the sun. Okay? It can describe any massive particle. But on the right-hand side, we have quantum mechanics. And quantum means very small. We have a quanta of light, which is a photon. Quantum mechanics describes all the subatomic particles like the electrons, bosons, neutrinos. We have this very, very well tested and established theory called quantum field theory. And it describes the interaction, the dynamics of all these small particles. So this is the problem right here. We have this theory that describes very big, and we have this theory that describes the very small. And one of the major goals, actually the major goal in physics, is to combine these two theories. We want a unified theory. So for any of those who are already aware of this quantum gravity, you probably think that we're not even close to getting a theory of quantum gravity. But this is actually not true. We've made a lot of progress actually into creating this unified theory of quantum gravity. And not many people think we've made progress, which is a big myth in the popular culture because it's not been talked about much. The year is 1998, and a man comes to the scene named Juan Maldacena, and he creates this almost magic correspondence called the ADS-CFT correspondence. And this correspondence links certain conformal field theories, which is the CFT, which is just a special case of a quantum field theory, which is quantum mechanics, and it links it to ADS space, which is a space that solves a solution to Einstein's field equations. So it links quantum field theory to gravity. And this correspondence says that there are very special cases of conformal field theories that have a direct correspondence. They're completely equivalent to theories of gravity. So for example, if we have just a plain vanilla quantum field theory with nothing in it, this is somehow exactly the same as an empty space-time, okay? Which is kind of weird if you think about it, because how is that possible? They're completely different. But it is via this Rosetta Stone, I guess. And if we have, for example, a photon in our quantum field theory, which is labeled by gamma, then that is completely equivalent to a gravity wave in our dual space-time. And if we have a lot of energy, if we have a lot of these photons, we have a lot of built-up energy, and the limit, it turns into a black hole in our space-time. So you can see this kind of crazy correspondence between quantum and gravity. And this was the beginning. This was the beginning of this crazy revolution. But the next question to ask is, how did this happen? Where does this ADS-CFT correspondence come from? The year is 2001, and my man Juan Maldacena is back on the grind again, coming up with some crazy theories. So he was playing around with this ADS-CFT correspondence that I just talked about, and he found something really interesting. So consider two separate spacetimes. We have one on the left over there and one on the right. And there's a black hole in each of these spacetimes. So we have two black holes, and if you study general relativity, you know that black hole has a region that is the maximally extended region of the black hole. And these two black holes are connected in this middle via this wormhole over here. But they're still two completely separate spacetimes, okay? And he showed that through this correspondence, that two separate spacetimes connected by a wormhole is exactly equivalent to this, via this ADS-C correspondence. It's exactly equivalent to two separate quantum field theories, but the catch is that they're entangled with each other. So this psi over here denotes the state of the system, okay, in those brackets over there. And the state is just going to be a sum of all the different states of the quantum system. So it's going to be a sum over what is called energy eigenstates. So we have, the first one is just empty quantum field theories, and then we have an excitation like a photon, and then we have more photons, and then we have black holes. So it's a combination of all these states that are entangled with each other. Here we're going to do a lightning review of quantum entanglement, and I'm just going to cover the very basics. So consider just one spin system, like an electron. An electron can either have spin up or spin down. And then in quantum mechanics, any state psi can be written as a superposition of these up and down states with some coefficients C0 and C1. Now entanglement comes from two spin systems. So let's say an electron and a proton, for example. And in this system, we have four what are called basis states. We have up, 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 down, down, up, and down, down. And entanglement comes from the fact that when we create a general state, we cannot distinguish from the first particle and the second particle. If we can't distinguish between the two, then they're said to be entangled. So some examples here. Non-entangled would be up, up plus up, down, because you can see that we know the state of the first particle because we can factor out the up from both terms. And as well, the second one is just obvious. But if you look at the entangled states over here, we have, for example, up, up plus down, down. Then we don't know which particle is A, which particle is B. We can't distinguish between the two. And in general, if we have a general state, then it gets even more complicated. And they can be very different many ways that the two particles can be entangled with one another. So in an ordinary quantum field theory, just a plain one as you can see up above, we already have entanglement present. If you look at the left side and the right side, they're actually going to be entangled with each other, even if there's no photons or anything in the quantum field theory. In the basic ground state, we already have entanglement present. So, in around 2003 to 2005, people were researching this entanglement, and they're seeing via this duality, via this correspondence, what it would show in the corresponding space-time. So just a plain vanilla quantum field theory in the ground state, it would correspond to just an empty space-time. But then if you start tweaking this quantum field theory and making it much less entangled, as you can see in Psi 1, it actually starts splitting the space-time apart via this correspondence. And if you keep doing it, if you keep less entangling it, it gets to the point where the two spacetimes actually rip apart from one another and they become two completely separated spacetimes. And that was very interesting. So we can see from this correspondence, we can make this really exaggerated statement that without quantum entanglement, without this entanglement of the quantum field theory, we have no gravity at all, no spacetime. So now we're going to take a little break and go to a completely different topic, which is going to be a geometry problem. And in this problem, consider a space called anti-de Sitter space, which is just a hyperbolic space. That's all you need to know about it. And consider 2 points separated by a distance L right next to the boundary. It has to be a little bit above the boundary because you can never really make it to the boundary because of the type of space that we're in. And we want to find the shortest distance between those 2 points. And it turns out, doing some fancy calculations, that this length, this arc length of the shortest distance is equal to some constant over 3 times the natural log of L over epsilon. And this is very important, so remember that formula. It was shown that the entanglement entropy, which is one way of quantifying entropy for a quantum field theory, so the entanglement entropy has the same exact formula as the length of the shortest distance between 2 points for a conformal field theory. So that's pretty crazy. So a geometry problem is exactly equivalent to an entropy problem. And geometry is directly linked to curved spacetime, to spacetime, as we saw before. So this is more proof that there is this deep connection between quantum mechanics and spacetime. And then a couple of guys called Ryu and Takiyanagi came to the scene in around 2006, 2007, and they showed that in higher dimensions for any conformal field theory, if we have a ball-shaped region, then the entropy, the entanglement entropy, which is denoted by S, so the entanglement entropy of any ball-shaped region is directly proportional to the area of the minimal area surface with the same boundary as A. So that's a lot to take in, but there's a good example with black holes that came actually many years back with Bekenstein and Hawking in like the 80s. They found that the entropy of a black hole was proportional to its area. And they didn't, this was shocking news, but now we really understand why. Because the entropy of any subsystem, the entanglement entropy, is directly related to this area of the minimal surface. So we're now seeing a pretty striking turn of events in physics. We've been trying to put quantum mechanics and general relativity together and make it into one grand unified theory for the longest time. But what we're finding out now is that they are just two pieces to the same puzzle. We've been trying to fit a square into a circular hole, but now we're seeing that they're one and the same, just two sides of a coin. And through this Ryu-Takiyanagi conjecture and the ADS-C correspondence, we're making a lot of progress towards this. And I'm really excited to see what's going to happen in the future.